Alrighty, welcome to the second semester of AP Statistics, and specifically we're starting here in Unit 5, which is called Sampling Distributions, and this is going to be the gateway into inferential statistics. So semester 1 was focused about descriptive statistics, how we describe samples, how we obtain samples, the likelihood of obtaining samples, etc. And we've seen this common theme of samples. Well, thinking back to Unit 3, we try to take representative samples so that we can generalize to a population, and a sample gives us some insight into the population. Now, we're going to be starting off with proportions, which is dealing with categorical data. So there are two types of things that we need here. The first one being a parameter, meaning that this is a characteristic of the population. Parameter describes the population. And here we'll use capital P, which stands for the population proportion, and typically size capital N. Now this is all relative. This just means that I'm looking at the percentage of people who are left-handed in the American population. I'm looking at the proportion of German adults that have blue eyes. I'm looking at the true population proportion of humans that identify as Christian, etc. Now, because populations are always changing, it's going to be very hard for me to obtain a true value. So I'm just going to go based on some evidence that I have. Now, we are typically used to dealing with statistics, and statistics describe the sample. So in order to describe the population proportion, we're going to use what's called p hat, the sample proportion, to describe the population proportion. So this will be lowercase n. Now, thinking back to Unit 3, we know that every time we take a sample, we are possibly going to get different results. Now, it is totally probable that we could get the same proportion or the same mean, but due to sampling variability, the more samples we take, the closer we get to that true value, but also each sample should be unique, should be different. But eventually, due to the law of large numbers, we're going to start seeing some of those same values repeat. Now, what is different here, so a sampling variability describes the variation from sample to sample. A sampling distribution, which is what we'll be focusing on, is a distribution of values for the statistic of all possible values from a given population. So we are using estimators to describe the population, and I have 4 instances here with me. So here is the truth, is the population parameter. This could be mu, the population mean, or p, the population proportion. And thinking back to when in Unit 3 we were taking random samples, because randomness helps to reduce the effects of bias, and thinking back also to stratification allows us to reduce variability, variation. But we can see here that each time we take a sample, and as we continue to take samples, things are going to happen, right? We learned about biases, we've learned about non-random sampling methods. So if we look here at the first one, we see that we missed the population parameter. Whatever method I was using did not capture it. And there is also a large amount of variability here. So you can see here that we miss it. So this distribution here is going to have high variability and high bias. Well, if we go down here, we kind of capture the population parameter. So I'd argue that that's low bias. But we can still see that the net that we cast to capture that parameter is still very wide. So that's still going to be high variability. Now, these aren't great because we're literally just throwing shots in the dark and hoping that they'll capture it. And in one instance, we do capture it, but in the other, not so much. So we go over here, we improve our variation, and we look here, and there's 2 distributions. Well, this distribution has low variability because there's not much spread in the distribution. But we look and we completely miss the population parameter. So we have high bias, which means we're looking for something with low bias and low variability, which that'll be right here, our golden nugget, our golden ticket. We see that this distribution, this sampling, captures the parameter, and it does so in a way that reduces the variation in that distribution. Now, all of this is a bunch of hoopla, so let's take a look at a real example here. And just as a reminder, when we're looking at the proportion or the sample proportion, we look at x over n, the number of successes in a sample divided by the sample size. So I'm going to look here at this distribution, and Reese's Pieces claims that about 40% of their candies are the color orange. And so here I have my population. This is all Reese's Pieces that exist. They get produced, they get turned into these little packages, and that's the ones that you and I consume, but they all come from the same population, from that distributor, that manufacturer. Well, I'm going to take a sample And in my sample, we're going to describe the sample, right? Thinking back to cusp, our center, unusual, spread, and shape. But then I'm going to keep plotting these samples to get an idea of what happens. So let's say I'm going to take a sample of 50, and I believe 40 of those pieces are orange. So I look here for my population, and I draw 50. And it looks like in this sample of 50, 24 of the candies are orange. Okay, well, that doesn't always mean that I'm going to get 24. That just means for that one sample, it was 24. So I'm going to take another random sample of 50, and it looks like, oh, I got 24 again. Okay, let's take another sample, and let's see. And this is so exciting, I know. Okay, 21. So let's suppose that I take, I don't know, let's go with 25 samples. So I'm going to draw the samples. I thought it went by a little quicker, my bad. So we're going to draw 25 samples, and we look here, and it looks like, okay, we're getting all sorts of different numbers. So from my population, I'm taking samples, and I'm now plotting those samples along here to form the sampling distribution. Well, let's suppose that I take a large number of samples. I'm going to take 1,000 samples. And right now I'm counting the number of orange candies in each sample. So we look here, and it looks as though, all right, so these are the number of orange candies in the sample. But I want to look at the proportion of orange candies. And remember, we look at the success over the sample size. Well, my n is 50. My x would be all of these different variations. So I'm actually going to convert this to a proportion. And if you look, there's not much difference between the number versus the proportion of orange candy. So this is my population, what I want to estimate. This is my sample. This is what I'm using to estimate. And if I keep taking samples in the long run, I believe that on average, there should be about 20. 20 would be the most common. 20 out of 50 is about 40%, which we believe to be true. So sampling distribution is essentially, we're just going to keep taking samples and samples until we get closer to the truth. So there have to be some conditions that happen here. And we call these conditions the sins of statistics. So here's my population proportion. And again, it doesn't always have to be people. It could be cars, it could be flowers, it could be license plates, it could be coins, who knows. But within my population, there exists a parameter, P, the true population proportion. And I'm going to continue to take simple random samples of size n, making sure they are the same. So I'll take a sample of 30, another sample of 30. I'm going to keep taking samples of 30 to get these p hats, the sample proportions. And if I go ahead and plot these p hats, eventually if I plot all possible samples, I take all possible samples of size 30, I would have a sampling distribution that looks like this. Now you might recognize this from our normal model days back in Unit 1. And you can see here that the different values of the statistic will be close to the true population proportion, and they'll have a spread that has this handy dandy formula. Now, no fear with formulas because these are all on our AP Stats formula sheet. So when you look here, section 3 now, we have these sampling distributions, and we're going to be focusing on this top row for one population. So here's our mean, and here is our standard deviation. So we do these things here. Now, there are 3 important conditions that we need for a valid sampling distribution. And I'm moving my face. Here we go. Now, I said the 3 sins because those are the order of conditions for it. So the first one, the S stands for stated random. We obtain our data either from a random sample or we come from a randomized experiment. Now, the next one, the I, stands for independent. And we do this so that observations are independent of one another when sampling without replacement. That means my first sample doesn't influence my second sample. My data doesn't influence your data. And we check this not by just assuming, but by looking at a condition called the 10% condition. And that just says that our sample size is less than or equal to 10% of the population size. And 10% is an arbitrary number. It just means that, I'm taking small samples and I don't want it to be any more than 10%. Because if I were doing 20%, let's say my population is small, I start doing 20%, I'm going to have some overlapping samples and people are going to be double counted. And if there's bias in that sample, no bueno. So we check the 10% condition to ensure independence between our observations. And the last one is we're trying to approximate the normal model. So we're looking that the successes and failures are at least 10 so that I can use a normal model when calculating it. And that's why we see here, this resembles our normal model. So we have 3 conditions, stated random, independent via 10%, and an approximate normal shape. And we'll check that by doing what's called the large counts condition, where I'm going to take the sample size and times it by the proportion to see if it's at least 10. And same sample size times it by the complement of the proportion to see if it's at least 10. Now, if these conditions are met, we will have the following sample distribution. Our sample proportion will be distributed approximately normal, assuming that we meet large counts, with a center of P, assuming we're using an unbiased estimator, and a spread here using this formula obtained if our sample is no more than 10% of the population. So we need to check those three conditions to verify our sampling distribution. Now let's look at an example here. The Gallup poll once asked a random sample of 1,540 adults, do you happen to jog? And we suppose that the true proportion of all adults who jog is about 15%. So we need to check our sins here. The first sin, did we obtain a random sample? And we did. A random sample of 1,540 adults was used. Next, we check the 10% condition, and I'd argue that it's reasonable to assume there are at least 15,400 adults in the population. All right, so now we check the large counts condition. So I'm going to check the number of successes and failures in the sample, the sample size times the claimed proportion, sample size times the complement of the proportion, and I'll take 1540 times 0.15 and the complement of that, and 231 and 1309 are both greater than or equal to 10, so a normal model is appropriate by large counts. Thus, I'm going to use these formulas here from the formula sheet, and all I'm using is P is 0.15, N is 1540. Plug these into the calculator, and I get that the sample proportion is distributed normally with a mean of 0.15 and a standard deviation of 0.0091. And again, each condition plays a role here. Here's my large counts condition, here's my random condition, and here's my 10% condition. So in theory, 1540 is not the only, this is one sample of 1540. I could take another sample of 1540 and get a completely different sample proportion and so forth, but I'm assuming the claim is that it's 0.15. So when I plot my data here, on 0.15, again, if I were to take all possible samples of 1540 adults, they would all fall within this normal model. Now, I want to find the probability that the percentage is between 13 and 17% of a random sample of 1540 adults that are joggers. So we just treat these like normal model problems. Really, the hardest part here is just checking the conditions and then describing the sampling distribution. But once you have that set, you're good to go. And you just basically solve like you would a normal model problem. So I want the probability that the proportion, the sample proportion, notice we're not using X, now we're using P hat, is between 0.13 and 0.17. Well, I'll convert both of those to z-scores and then find the probability that an observation has a z-score between these two. We take the difference, and using my table A from our formula sheet, we get there's about a 97.22% chance that in a random sample of 15 adults that there will be somewhere between 13 and 17% that are joggers. So very likely, right? Thinking back to the empirical rule, the 68, 95, 99.7, this, they're both within two standard deviations. So that's about a little bit over 95% of the data. All right, now a big thing on the AP exam is the violation of conditions. And here it says, what size sample would prevent us from using a normal model? Now remember, in order to use a normal model, the successes and failures both have to be 10. So to not use a normal model, they'd need to be less than 10. So I just do some substitution here. And if I had 66 adults, if I did 66 times 0.15, it would not be 10. And I could not assume that the shape of the sampling distribution is approximately normal because this violates the large counts condition. So that's just going to have to be one thing that you consider is, yes, it's the AP exam, so most of the conditions will be met, but sometimes they're not always going to be met. So here you go. Here are some example problems for you. So go ahead and pause the video, try them out, and then we'll go over the answers shortly. All right, so hopefully not too complicated. We see here, I'm not always going to make you write out the conditions because sometimes these are multiple choice questions. We'll address the sampling distributions using inference at a later time, but I won't be mean. So when we're doing problems like this, you can just go ahead and make notes here. Notice these are not complete sentences. So on the actual AP exam, this would not fly, but it's okay. We're just practicing. So if you did this correctly, your conditions should have been met. You should have had this sampling distribution, and you should have gotten about 0.9573. Then here in the multiple choice question, the answer was choice C. So that's a little bit more about a sampling distribution for a sample proportion. And over the next few days, we're going to practice and we're going to look at two sample inference as well. So I hope you learned a little bit more about a sampling distribution for a sample proportion.